Okay, class. So the next thing that we're going to talk about basically has to do with, since we're interested in the electrons, where are the electrons? The electrons are, of course, in the orbitals. So this is just a basic review of the orbitals that we're going to find electrons in. So atomic structure. So how are electrons distributed in an atom? So we went through a series of different models in Gen Chem 1, and at the last stage, we were talking about the quantum mechanical model of an electron. So how electrons behave was basically described by the Schrödinger equation, so a mathematical expression, the Schrödinger wave equation, and that equation can be somewhat difficult to solve. In fact, you can only solve it for the hydrogen atom. But also, it can conceptually, it's quite difficult to actually to wrap your head around it. So the solution to this wave equation is what we call a wave function or an orbital. And the nice thing about these is that it's something which is which you can visualize really simply. So when you actually plot this 3D shape of an orbital, it's going to tell you where an electron spends 90 to 95% of its time. So it's a probability. The probability that you're going to find an electron in this space is, you've got 90 or 95% confidence, and it's much easier to see. So the orbitals themselves. So what we did is we talked about this from a quantum number. Remember, every electron had a unique set of 4 quantum numbers, and one describing the energy level itself, one describing the atomic shape, one describing its orientation in space, and the last describing the electron. Is it spin up or is it spin down? And so having a series of numbers on a page, kind of hard to visualize what's going on, but it's really easy to see what an s orbital looks like. An s orbital looks like a beautiful sphere. A p orbital looks like this dumbbell shaped system, and it has got some directionality to it. So it can follow the Cartesian coordinates. So x-axis, y-axis, z-axis. So it's got directionality to it. And then there was a series of d orbitals, which looked essentially like 4-leaf clovers, with the exception of one which looked like a p orbital with a little belt around the side of it. So in organic chemistry, the nice part is that the orbitals that we're really interested in are going to be, because carbon's on the second row of the periodic table, is really s and p. So those are the two we've got to worry about. We're rarely going to talk about d orbitals in any sense. And the thing to remember also is that for each given orbital, it can hold 2 electrons, and they'll have opposite spins, so spin up or spin down. These orbitals themselves are organized in different layers or shells, getting further and further and further from, or higher and higher in energy, which loosely equates to distance from the atom itself. So excessively large size and energy. So it's quite a bit less complicated because we're just viewing, like we're visualizing stuff as opposed to having a bunch of numbers on the page. So we would have talked about s orbitals being spherical, nucleus is at the center, p orbitals being dumbbell shaped, and the 3 types that I mentioned before, y, x, and z. And the nucleus for a p orbital is right sort of in the middle, in between these 2 lobes. And the interesting thing about a p orbital is that there is a plane where the probability of finding an electron is 0. So there'll be what we call a nodal plane, which bisects this the dumbbell, and you're gonna, there's no electron density there, so you're not gonna find an electron in this plane. And this is gonna become important later on when we're talking about certain types of bonds. Because the p orbital has got two lobes, one is usually depicted as a shaded color, in this case green. And back in the day when I was a student, uh, they depicted these as positive and negative, which was super confusing because there should be no positive here, right? It's a phase. So what we're going to see is that for these orbitals to make the appropriate bonds, they have to be in this correct phase with one another. So green's got to interact with green. The non-colored has got to interact with the non-colored. That's what this means. But having positive and negative was just super confusing. I remember I was always confused by that. All right, okay, so now, so here's a little energy diagram here. We got our 1s orbital, we got our 2s orbitals, our 2p orbitals, and then the next layer up would be the 3s, 3p, 3d. And so first shell, second shell, third shell. And depending upon your outer, remember, your outer electrons are involved in the bond making and the bond breaking. If you fill a shell, a lower energy shell, we call these core electrons. So in the case of 1s, there's 2 there. The core electrons are not involved in any sort of the bond breaking. It's the ones in the outer shell, which in this case would be the second. These are what we call the valence electrons. So these are the ones that would be involved in bonding. Now, it just turns out that the electronic configuration I've got drawn here is that of a noble gas, and it wouldn't be particularly, it'd be inert to most things. Okay, so we went through a process of writing out the ground state electronic configurations, and they followed basically 3 rules or principles: the Aufbau principle, Pauli's exclusion principle, and Hund's rule. So Aufbau principle basically says that you put your electrons in the lowest energy available orbital. So you put them in the lowest first and fill up from the bottom to the top. Now, the Pauli exclusion principle basically says that you can't have 2 electrons that have the same 4 quantum numbers, which in our case becomes spin. Is it spin up or spin down? So in this diagram above, this little arrow pointing up, that represents 1 electron, and it is spin up. For another electron to be in this orbital, it has to be spin down, or else it would violate the Pauli exclusion principle. So once this has got its 2 electrons, it filled, and then we'd have to fill the next orbital up, which would be the 2s. And you keep on going. So if we had 1 more electron to fill in this thing we have in this system here, it would go into the 3s orbital. Now, Hund's rule, this applies in scenarios where you have got 3 orbitals that have got the same energy. So we call these degenerate orbitals. So in the case of nitrogen here, nitrogen's atomic number 7. We've got 7 orbitals, 1, 2, 3, 4. And then we've got the 2p orbitals, and they all have got the same energy. Hund's rule says that you place these electrons with the same spin, and you fill up the different orbitals first. So if this is a spin up electron, then you'd put the next one in this orbital, and then the next one in this orbital, and they'd all be spin up. What we're gonna, like for most, like we're not gonna, this is the, yeah, so that's basically Hund's rule. We don't see this very often. The time where we do see this involves molecular oxygen, and that's important in radical reactions. All right, that ends that.